Hi students, this is a new lesson, mechanical properties of fluids. The previous lesson was mechanical properties of solids. There we studied about stress, strain and Young's modulus, rigidity modulus, bulk modulus. That means how a body deforms under the application of stress on it and which type of strain it may produce in it because of different stresses. So that we studied about solids. Now, what about these fluids? Whether they undergo strain or not when a stress is applied on it. So what is the behavior of solids under these stresses? So this is called mechanical properties. Now, first of all, to study about the mechanical properties of fluids, we should know the difference between a solid and a fluid. So in a solid, so this is a solid. We know the molecules are fixed and they are packed tightly. Molecules are packed tightly. If you apply a force here, tangential force, this is a tangential force acting parallel to one of the surface. So here, let me take one book here. So this is a tangential force, mathematics textbook. Now, this is a solid. If I apply a force here, just to observe these layers here, layers of the solid. If I apply force here, they are displacing, the layers are displacing here. But if we apply a similar force on a liquid drop, then what happens? Instead of sliding one over the other, all the layers will flow and the velocity acquired by them will be more. That means here, due to this application of this tangential force, so this substance will change its shape. But what about the molecules? Molecules will move a little bit, some molecules. But these molecules which are at the bottom will not travel too much because the force is tangential. The effect of force will be more on the upper surfaces, upper layers, and this effect will be less at the lower surface. But if you apply that same tangential force on a liquid, so when a force is applied here, tangential force, here these molecules will move here, these molecules will move, and almost these molecules also will move in different directions. They may move generally in the direction of the applied force, but here this will flow, all the layers will flow here. So what is the main difference between a solid and a liquid or gas? Why? Because fluids means the substances that can flow easily under the application of force, that is tangential stress, are known as fluids. So fluids can be divided into two parts here. One is liquids and second one is gases. So under the application of these stresses, what is the behavior of these fluids? That we study as mechanical properties of fluids. Reason behind this behavior of fluids and the behavior of solids is here these molecules can attract with each other with a large force. Similarly, these two molecules also will attract with each other. These two molecules attract each other. These two molecules attract each other. So all the molecules will attract each other. Now, if it is the surface on which the force is applied, the forces will be present parallel to the surface as well as perpendicular to the surface. So in solids, both parallel to the surface as well as perpendicular to the surface. That means forces are available, are present both parallel as well as perpendicular to the surface of the body. But whereas in a fluid, what happens? Remember, these two attract with each other perpendicular to the surface. But parallel to this one, this force is absent here. So, force parallel to the surface is absent. So, when this force is absent, generally what happens? These two will try to attract with each other. Perpendicular to the surface or perpendicular to the force, this will attract with each other, but these two will not attract with each other. This will try to move in this direction, this may move in this direction or in another direction, because no force of attraction between these two. That's why generally whenever force is applied, the perpendicular force will be present. Perpendicular force perpendicular to the surface is present here. So that's why, remember students, if you take a container and if you fill this with water, not only water, any liquid, here these water molecules will exert force perpendicular to the surface. So this is the surface, so perpendicular to the surface forces will act, but parallel to the surface forces should not act, will not act. That's why always what we can write, fluids exert force perpendicular to the surface in which they are in contact. So fluids, either solids or liquids, fluids exert force always perpendicular to the surfaces in contact. Now, about these mechanical properties of fluids, first of all we should have some idea, some knowledge about some of the physical terms that we are going to use in this chapter. The first one is density, generally denoted with a letter rho, R-H-O, rho, a Greek word. So what is this density? Density is the mass of substance per unit volume. So now density can be written as mass by volume. This is the density. M is the mass and V is the volume. This may be small m by small v or dm by dv. So these are the different formulas that can be used here. If you take a small mass in a small volume, that we call it as a density. And this is mass, total mass of body, total volume, that is also density. This is a big mass by big volume, this is also density. So now what is the SI unit of dimension formula for a physical quantity? So now I am going to write, the mass is measured in kgs and the volume is measured in meter cube, per meter cube. So kg per meter cube is the SI unit for this one, and the dimension formula mass is m and the dimension formula for volume is L cube. You can write m power 1 L cube t power 0. So this is minus L cube, or you can just write m L power minus 3. So this is the dimension formula for density. Now what is this density? The mass present for unit volume. Suppose if we construct a tank with the dimensions like this, so this is a tank constructed here. The length of this tank is 1 meter, width is also 1 meter, height is also 1 meter. Now what is the quantity of mass of the substance that can be filled in this tank? Suppose if you take ice, remember students, if you take ice, if you fill the entire tank with ice, it is found that 920 kgs of ice can be filled in this 1 meter cube volume. Why? Because volume is equal to length into breadth into height. This is 1 meter into 1 meter into 1 meter. So volume is equal to 1 meter cube. So this we call it as unit volume. So here also while defining this one I used this word unit volume. So what is density? It is the mass of the substance per unit volume. So in this unit volume, what is the quantity of matter that is present? Here quantity of matter is nothing but mass of the substance. Now it is found that 920 kgs of ice can be filled in this one. Now if you remove the ice and if you fill this tank with water, it is found that exactly 1000 kgs of water can be filled in this tank. Similarly, if you fill this with blood, it is found that 1060 kgs of blood can be filled in this one. Similarly, if you take steel, nearly 7000 kgs of steel can be filled in this one. And if you take mercury is also a metal, The only metal in the liquid form is mercury. So it is found that 13,600 kgs of mercury can be filled in this one. And similarly, if you take this platinum, nearly 22,600 kgs of platinum can be filled in this one. So these are the different masses of the substance in the same volume. And similarly, if you take our nucleus of any substance, any atom, if you take, this is atom, this is the nucleus. So nucleus generally will have 2.3 into 10 power 17 kgs. That means if you completely filled with this box or tank with all the nuclei, that means any type of nuclei, all nuclei will have same mass, so per meter cube. So this is the density of nucleus. These are the different values. Actually we need to remember this value as well as the mercury value. Why? Because sometimes they won't give these values in problems. So please remember, density of ice is, density means the mass of the substance per unit volume. So I am going to write density of ice is equal to 920 kgs per meter cube. That means in 1 meter cube we can have 920 kgs of ice. So density of water is exactly 1000 kgs per meter cube at 4 degrees centigrade only. If temperature changes, this value slightly changes. That we will discuss in the next lesson, that is the thermal properties of matter. Similarly, density of mercury, this is around 13,600 kgs per meter cube. So these three values are very, very important. Relative density, also called specific density. So this is a relative density. What is this relative density? It is the ratio between density of a substance with the density of water. Why? Because water has a complete number here. That's why every time when we are comparing the density of one substance to water, we will get a number. So it is easy to remember that number instead of remembering all the densities of all the substances. Now, what is this relative density? So I am going to write this as RD, relative density or specific density. This is a density of substance by density of water. That means we are comparing density of a substance with respect to density of water. How many times this density is more than water? How many times this density is less than water? So here, now let me take this ice only. So what is the relative density of ice? So relative density of ice is given by density of substance, that is ice, by density of water, that is 1000. Now cancel these two, this will become 0.92. So what I am going to write here, there is no unit because this is kg per meter cube. This is also kg per meter cube. These two get cancelled. So all these relative values will not have any units here. So relative density is 920 kg per meter cube by 1000 kg per meter cube. Kg per meter cube can cancel. So this is a pure number only. So relative density is a pure number. So what is the meaning of this one? The density of ice is 0.92 times the density of water. Similarly, what is the relative density of mercury? This is the density of mercury, 13,600 by density of water, 1000. So this will become 13.6. This is a pure number. So the relative density of mercury is 13.6. The meaning of this one is, the mercury density is 13.6 times more than density of water. Now, if you know this relative density, now you can find the density of any substance. So the density of any substance is equal to multiply this relative density into water. In a problem, instead of giving the density of a substance, for example, let me take blood only. So here blood density, actually I wrote there 1060. So this is not 1060, this is 1600. So this is 1600 kg per meter cube. But instead of giving this value in a problem, they may give the relative density of blood is 1.6. So what is the density of blood? So if you know this relative density 1.6, this is the density of blood by density of water, that is 1000. So what is the density of blood? Multiply these two, you will get 1600 kg per meter cube. So we have to remember this formula to find the density of a substance. If you know its relative density, just to multiply this with water, you will get the density of that substance. Sometimes we need to remember the relative density of gases or density of gases also. Why? Because this is the mechanical properties of fluids, not only the liquids. We need to remember density of gases. Now if you take the density of air, so if you fill the same tank, here already I have explained this one, a 1 meter cube tank, 1 meter, 1 meter, 1 meter. If you fill this with air, so what will be the mass of this air? 1 meter length, 1 meter width, 1 meter height. This is from here to here 1 meter, from here to here 1 meter, and height is 1 meter here. And if you fill this entire tank with air, it is found that air has mass which is equal to 1.29 kgs per meter cube. So this is called density of air. So the density of air is given as 1.29 kg per meter cube. Suppose if it is a CO2 gas, the density of CO2 is around 1.97 kg per meter cube. Generally, we are interested to learn only about the density of air. Why? Because in this lesson, we are going to find the pressure created by air. So while finding the pressure of air column in a particular problem, we need to remember this formula also, this value also. So density of water, density of air, density of mercury are very, very important. Now, so after this, the second one is pressure. So as I said earlier, if you fill a tank with a liquid, this is a tank filled with a liquid here. Here, the molecules of the liquid will exert pressure perpendicular to the surface. That is the main difference between the solid and liquid. So the pressure is the force exerted by this liquid on the surface of this one. So pressure is the force exerted by a liquid on a surface. So pressure is given by force acting per unit area. So this is the formula for pressure. So what is this pressure? So we can write the SI unit and dimension formula for this one. So what is the SI unit for pressure and the dimension formula for pressure? So pressure is force. Force is measured in Newton and the area is measured in meter square. So this is Newton per meter square. This is also known as Pascal. It's the name of a scientist. So this is also known as 1 Newton per meter square is also called 1 Pascal. Now the dimension formula, force F is equal to ma, that is m is mass, a is acceleration, Lt minus 2. By capital A is the area, so which you can write it as L square, L and L get cancelled. M power 1, L power minus 1, T power minus 2. So this is the dimension formula for pressure. Now, what are the areas that we are using this pressure daily? Now, you just see this example. If you take one block here, wooden block, or let me take one sponge here. If you keep some weight here, this is a weight, a block. So this is a block of 100 newtons. So whenever the weight is placed on a sponge, what happens? The sponge will have some strain. That means so it will deform its shape. So here this is called a change in shape of the body. So here and there is some elongation along these lengths also. That means change will change. That means there will be a change in the shape of the sponge. Now if you take the same sponge here on the same surface here, and if you keep a knife here, a sharp knife, very sharp knife, which is having 100 newtons force. This sharp knife can cut this sponge here. So here also I am applying 10 newtons force, but here also the force acting on this sponge is 100 newtons only, 100 newtons each in this case. But why it is able to cut this one and why it is not able to cut this sponge into pieces? The reason is, whenever the area in which it is contact with the surface is less, the pressure created will be more. When the area is less, the pressure created for the same force. That means the same force is doing two things here. That means it is showing one type of property here and it is showing another type of property here. That means the effect is different. Here in the problem diagram 1 and diagram 2, the effect in the first one is different. It is just deforming the sponge, whereas in the second one it is cutting the sponge. So here pressures can be understood by the effect of force on a particular area. The same example, if you want to walk in sand, especially in deserts, so we need feet which we have to apply small force. So our weight is acting like this. So when our weight is acting like this, remember students, this is our weight mg. Sand cannot give an equal and opposite force on our body. That's why generally we would like to walk slowly on the sand, so that we will try to reduce our apparent weight. Due to this, this force will be less, so that our foot will not penetrate into the sand. Whereas if you take a camel, so if you take the feet of the camel, so the area of the camel foot will be too large when compared to the area of our feet. So why it is provided like this? This is the leg of the camel. So here you can see this is the feet. When the area is more, same process, when the area is more, for the same load, the pressure will be less. The weight of the camel is too high here, but when the weight of the camel is too high, total force is acting on these feet only. That's why, so the feet are designed such that the total weight is acting downwards, but as the area is more, it will exert less pressure on the sand, so that these feet cannot penetrate into the sand. This is why the feet are made large here. Similarly, if you take the railway track here, you can see the sleepers just below the railway track. So if you remove the sleepers, what happens? When a train goes on this track, the total weight of the train will act on the track, and the track can penetrate into the earth. But as the sleepers are provided just below this one, so here we are increasing the area of contact between the earth and the track. So as the area of contact is more here, the pressure will be less for the same force. So when the pressure is less, the track will not penetrate too much into this earth. And you can see when a train is moving on a track here, you can see some deformation in the track that you can observe clearly. But this deformation, as this steel track is having that elastic property, what we studied in the previous lesson, so they regain their original position whenever the train, that means the deforming force is the weight of the train only. When the train goes here, once again it reaches its original position. You see, the mass is a scalar quantity and volume is also a scalar quantity. So if you divide a scalar with a scalar, always you will get a scalar. So density is a scalar quantity. But now you see this pressure. If you take a container, if it is the liquid inside the container, and if you see the pressure at a particular point here, at this point, force is acting like this and the area is also acting in this direction, area vector. So in this area vector is normal to the surface. So at this point, force is a vector, area is a vector. That means the ratio between these two vectors may be vector or a scalar. Here, at this point, the pressure is acting in a particular direction. So let us say pressure is acting in this direction, P1. But what is the direction of pressure here? This is force, this is area vector. So let us say this is force is acting perpendicular to the surface. But here, the force is acting like this, area vector like this. This is pressure P3. So here this is P4. Here this is P5. That means at different points, pressure is acting in different directions. That means at a particular point, we can consider pressure as a vector. but in this entire container, pressure is acting at different points in different directions. That means if a physical quantity acts different directions at different points, then this can be called as a tensor. So please write down this one, tensor, a physical quantity that acts in different directions at different points. Different points of application is known as a tensor. So pressure can be considered as scalar, but exactly speaking, pressure is neither scalar nor vector. It is a tensor. Pascal's law, it states that the increase in pressure at any point on the enclosed liquid which is at rest is transmitted equally to all other points of the liquid and also to the walls of the container if you neglect this gravity. That means the Pascal's law can be applied only if the gravity is neglected. Now let me take one container here. So in this container I am going to take some liquid. So this is the liquid. So now the liquid is at rest. So here the mechanical properties of fluids can be divided into two parts. One is a study of fluids at rest, the other one study of fluids in motion. Just like a study of bodies in rest is called statics, study of bodies in motion is called kinetics or kinematics. Here this we are going to study about the density as well as pressure only if the fluid is at rest. Fluid is at rest. So also this topic, this part is also known as fluids at rest. So this is hydrostatics. So this part of this lesson, first part of this lesson is hydrostatics, that is fluids at rest. Here when the fluid or the liquid in this example is at rest, if you increase pressure at any point, so to increase the pressure we have this formula, force by area. So I need to apply some force per unit area. So now here if I apply some pressure perpendicular to the surface of liquid, so here pressure will increase. This pressure will will travel, transmit in all directions to the all parts of this liquid, and here pressure will increase. So let us say here pressure increased by 1 Newton per meter square. So what is the increase in pressure at this point? 1 Newton per meter square. What is the increase in pressure? Previous pressure may be anything, but the increase in pressure at this point will be 1 Newton per meter square. Here 1 Newton per meter square. Here 1 Newton per meter square. Here 1 Newton. That means you see this Pascal's law statement. The increase in pressure at any point of the enclosed liquid, remember it should be closed here, it should not open. If it is open, then we cannot use this one. So here if you take a rubber balloon here and if you fill the balloon with water, let us say now I am going to take a balloon instead of a container here. So like this is a balloon which is filled with some liquid. Now, if you apply some force perpendicular to the surface of the balloon on a particular area, so pressure is P is equal to F by A. Let us say this pressure is exactly equal to 1 Newton per meter square. If you press it, that means I am increasing pressure there. So here the increase in pressure is 1 Newton per meter square, here 1 Newton per meter square, here 1 Newton per meter square, here 1 Newton per meter square. So Pascal's law can be applied for an enclosed liquid which is at rest. Now this increase in pressure will be transferred equal to all other points. Any point, if you take any point here, at any point, the increase in pressure will be equal to the increase in pressure at that particular point where we applied the force. And also it is equal on the walls of the container. Here balloon is the container. So on the walls of the container also the increase in pressure will be 1 Newton per meter square. So due to this, if you apply a small force here of 1 Newton on 1 meter square area, this pressure will be more on all the walls. That's why if you press it more pressure will be created. Due to this balloon may burst. So this is a Pascal's law. Now how to prove it? Now for this proof of the Pascal's law, let me take a container here. This is a container which is filled with water. Instead of this one liquid every time, I am just considering this as water only. So in this what I am going to take, I am going to consider a small portion of it, a triangular portion here. So this is a small triangle portion. Remember, this triangle is not this much. This is a triangular prism. It is a small triangular prism, but to observe this one, I am taking a triangle prism like this, a small portion. That means this triangle portion is filled with water only. Now here you can see now the same triangle prism I am redrawing here, a bigger one here. If the area of this face is A and force acting is F, so I am going to write this face area as AA. That means this face is A and this face is B, this face is C. Now let the force acting here is FB, force acting on this surface, bottom surface is FC. Remember, once again I am telling, these three are very close to each other, just almost at a single point. So actually this is a single point, but from that I am taking a small prism. So I am drawing a bigger one here and enlarged version of that one. Now here, if it is the area, we know that if it is FA, that is force at point A, this can be resolved into two components like this, horizontal and vertically. If it is theta, what is the force here? This is FA cos theta. The component which is nearer to this theta will be cos theta component, and this will be FA sin theta. Similarly, we know that this is area. This is area. Area is a vector whose magnitude is AA. So now this is area vector AA. So this can also be resolved into two components here. As it is theta, this will become theta. This is AA cos theta. This is AA sin theta. So actually I am showing only one force that is acting on this surface, and these two forces can be resolved, can be written in terms of this one. So what is FB now? FB is the force which is equal and opposite to this one. So in place of FB you can write FA sin theta, same force. It is acting along x-axis, this is acting along negative x-axis, these two forces equal and opposite. So this will become FA sin theta. If area vector is A and this side is B, AB, but AB is this one which is equal to AA sin theta. Both are equal and opposite. Similarly, what is FC? FC is acting upwards, but what is the force acting downwards? These two are equal and opposite. As this liquid or this water is at rest, net force must be 0. So why it is I am taking this as a rest? So that means this Pascal's law can be applied only for the liquids which are at rest. Here, when this liquid is at rest, if you take any point, each and every point will be in equilibrium. So here, the component of this force is acting downwards and this force is acting upwards. So FC is equal to FA cos theta. Then only the particle which is at this point, present at this point, will be in equilibrium, means it will be at rest. Similarly, the area vector of this one is AC. AC is given by this component AA cos theta. Now we have 3 points now, at A, at B and at C. So I am taking those 3 points here, at A, at B and at C. So this is point A, this is point B, this is point C. Actually speaking, all these 3 points are joining at a single point only, very nearer to each other, a single point. Now at A, at B and at C, this is A, this is point B, this is point C. So what is the pressure at A? Pressure at A is equal to force acting on surface A by area of the surface A. And what is PB? PB is given by, this is PB P at B is given by force at B by area of the surface at B. And similarly, what is FC? So FC is PC is given by FC by AC. So I'm going to write this as at C. Pressure at C is given by FC by AC. Now, let me substitute this one. So what is PA? PA is given by force on A by area of A. So this is FA by AA only. So this is equation 1. So what is FB? FB can be written first PP is equal. FP is nothing but force at B. So this is FB, which is given by FA sin theta. So this is FA sin theta by what is this AB? So AB is nothing but AA sin theta. You can cancel this sin theta and sin theta. So what is PB now? PB, let me come later. Now let me see this PC now. So PC can be written as FC. What is this FC? This is FA cos theta by AC is AA cos theta. So these two cancel with each other. Now what is the final terms that you can write here? Pressure at A is equal force at A by area at A. So this is PB is equal, these two can cancel, force at A by area at A, and this is PC is equal force at area by area at A. You can see the pressure at A is equal to pressure at B is equal to pressure at C. So from this we can say the pressure at a given point in a fluid which is at rest is always constant. At that point pressure never changes.